Hey robot, I want a drink. Can you please help me? Hi, I'm Ilya, and today I will be exploring how large language models can control this robot to test the embodied reasoning capabilities. I've created an MCP server that allows any LLMs like ChatGPT or Gemini or Claude and so on, and any LLM client to control this robot with very easy plug-and-play integration by using information about the robot state and feed from the cameras that this robot has. I primarily did it as an educational experiment, so MCP is not the best and most efficient way to control the robot. So yeah, mostly it's for the fun and some education and learning. But on the way, I also explore a lot of different things like inverse kinematics of the robot, the overall implementation of keyboard control, testing of different stages of using letting MCP to control the robot. Also, I will talk about the MCP itself. So what is this? What does this protocol means and how to use it? So on so forth. So I actually go into a lot of details that can be useful in other projects, in other ideas and implementations too. In the first part of the video, you can find a lot of interesting and useful information related to LLMs and robots. And in the end, in the second part of the video, I will show a lot of demo of different LLMs controlling my robot. I will show both successful examples and fails, and also discuss the main fail patterns. All my code and instructions are available in the GitHub repository, so you can try it yourself at home and let me know how it goes. And now, let's begin. Let's take a moment to discuss what MCP is. MCP, or Model Context Protocol, is simply a standard for tool calling for LLMs. LLMs, in their vanilla state, can do only one thing. They can predict the next word in the text that you provide to these LLMs. And different techniques allows to create some wrappers on top of it, and also let LLMs to call different tools. Like they can change files on your computer, like the AI coding assistants do, or they can search in the internet, or can do a lot of different things. Actually, I don't think anybody thought about controlling robot using MCP when they developed this protocol, but technically it is possible, so we can do it. So this is why I decided to do this experiment and try it. But now let's go a little bit deeper and look at the examples of how LLMs work, how tool calling in LLMs work, and where MCP stands in this picture. To understand what MCP is, we first need to discuss how LLMs work and what is function calling. So first of all, the vanilla large language models can do only one thing. So the only thing that they can do is predict next word in the text. So basically we can provide them text and they can predict the next word in this text. How do they actually work? For example, how ChatGPT, Gemini, or Claude answer your questions when you ask them. Let's say that you ask LLM, what is the capital of Thailand? What happens inside LLM at this moment? First of all, the LLM has some system prompt that is simply some text that describes what this LLM is supposed to do. For example, it says, you're a helpful AI assistant, you should answer the user's requests and so on and so forth, and then give some extra instruction, and in the end it says, below is your chat with the user. And when you send some question to the LLM, your question is just added to the end of this text. It says, user asked what is the capital of Thailand, and then assistant should answer something. And this whole text that includes both system prompt and the history of your chat up to this moment is sent to LLM. LLM is trained on a lot of textual data, and it has some probabilistic model inside it that can predict what is the good word that can follow after the text like this. And it starts to predict these words one by one. So technically it predicts tokens, but for simplicity I'm saying words. And let's say in this case it predicts there, then it's appended to the text, and we do prediction again. The next word is capital, then off, Thailand, is, and finally Bangkok. So word by word is just predicting what is next. It's just predicting what is the highest probability word that follows the whole text that it was just presented. And eventually, when it's finished, when it indicates that the answer is finished, this answer is simply copied and sent back to the user. And this is how it works. And user get the answer that capital of Thailand is Bangkok. But what happens when LLM doesn't know the answer? So quite often you may see that, let's say you ask ChatGPT some question, ChatGPT doesn't know the answer, but ChatGPT search internet and gives you some answer from the internet. So how does it work? Let's say you want to give your LLM some extra capabilities on top of prediction of the next. In this case, you do what's called tool calling. And for simplicity, let's say that somewhere in the system prompt, somewhere inside system prompt, you add some text like this. If you need to search anything in the internet, just return search token and your request, and then the rest of the system prompt follows. And then when the user sends you the question, this question is simply appended to the end of this text. But now LLM has this information in context that actually it can return some search token and some search results will happen. So in this case, if LLM doesn't know the answer, for example, and cannot generate it from the data, or simply predict that generating this search token is just better option than making some random prediction of random word, it will generate something like this: search token, request the capital of Thailand. And what happens at this moment, the result of this text generation is not sent to the user. Instead, it goes through some tool that parses every generated response from LLM and checks if there is this search token or any other tool tokens were mentioned. And then if it identifies the search token, it takes the information that goes after it in the brackets and realizes that the search engine tool was called by the LLM, and simply sends the specified request to the search engine. So this tool logic is not LLM, it's just a simple code that parses text input generated by LLM, and if it finds some special tokens, executes some logic that written in this code. And in our case, this logic says to send text request to the search engine. And this text request is the capital of Thailand. Then search engine, it can be Google, Bing, whatever. It makes some search and generates some search results. Then combine the top, let's say, 10 pages of the search results, transform them into pure text so LLM can understand it. And then this tool wrapper that we have, send it back to LLM. And again, it just added to the context that LLM is seeing. And now somewhere in this prompt, in this long prompt that LLM can see, we have this information from, let's say, Wikipedia that says Bangkok is the capital and the most populous city of Thailand. And now we again ask LLM to generate the answer from assistant, but this time, again, as this information is already in the context, with the high probability, LLM will know what to answer. And LLM will simply generate the correct answer that the capital of Thailand is Bangkok, and this answer will be sent back to the user. So this is how it works. It's of course very, very simplified. In practice, it's slightly different, but the idea is very, very similar. So we simply train our model to generate some special tool tokens instead of just text tokens, and then create some simple parser that can check if this tool token was generated. And if it was, it adds some extra logic outside of LLM and then return results of this logic into LLM. So this is called tool calling, and it actually exists for quite a while. As long as all these LLMs became a thing, there were a lot of attempts to create tool calling, and all the big LLM providers created their own standards for tool calling, and it actually kind of works already pretty well in many different systems. MCP is simply the standardization of this tool calling mechanics. So what is the problem with tool calling? As I said, everybody already implemented a lot of tools before, but every creator of LLM implemented this tool in their own way. They use their own prompt, they use their own logic, they use their own model fine-tuning to teach model to use these tools. And as a result, a lot of these tools were not compatible to each other. So if you have some tool, some nice, let's say again, search engine, and you want to integrate it with LLM, you need to integrate it with all LLMs. If you are a creator of LLM and there are a lot of search engines that you want to use, again, you need to create the integration with each of them separately. And MCP is simply a protocol that was proposed by Anthropic, the creator of Claude LLM, that proposes the standard way to use tools across different LLMs. Technically, it's the same tool calling, but again, the feature of it is that it works just out of the box. Whenever a user interacts with LLM, they usually don't interact directly with LLM, with the model. They use something called a host. So it can be some application, it can be ChatGPT tool, it can be like Cursor or Windsurf IDE or something else. And this host uses LLMs. And also this host is supposed to implement this MCP client to support this protocol. And if MCP client is implemented, then the only thing that we need to do to integrate our service into LLM and give LLM extra capabilities is to implement what's called MCP Server. So MCP Server is simply some code, in my case it will be Python code, that implements some functionality. Again, in my case, this functionality is robot control, and do it in some specific format. So we implement these different tools that can control our robot, like get robot state, open gripper, move robot somewhere, and so on. And by wrapping this function into MCP server, we allow any LLM, any client, any host that supports MCP to use these tools. What we need to do is to set up the connection between MCP server and MCP client, and that's it. Everything else will happen automatically. So whenever we connect MCP server, MCP client will automatically get all the descriptions of all our functions, add the descriptions to the prompt that LLM can see. And if we ask some question related to, in our case, robot, for example, if user asks to open the gripper, LLM will see that actually it has function that called open gripper, and what it does is open gripper. And if it wants to do it, then it need to turn some special token and specify what exactly it wants to do, and so on and so forth. So LLM at this point will know what to do. And the main point here is that we don't really need to care about this part. We don't need to care about how LLM interprets all these comments. We don't need to integrate it with the client itself. We just need to set up very simple connection, just basically provide the address of our server to MCP client, and it will work. And this is the kind of best thing about MCP so far, is just you implement it once and then you connect to many different services, to many different clients, many different programs. And today I will show you how it works with different integrations and what the results. Let me introduce this robot that I will be using. It's called Standard Open ARM 100, and it costs a bit more than 100 USD. And I have a long video about it, and where I describe how to start using it and experimenting with this robot. So you can just follow the link and watch it. I will not repeat myself here. I will just say that this robot has 5 degrees of freedom plus 1 extra degree to control the gripper. Also know that recently the robot released the next version of this robot called SO ARM 101, but it's very, very similar. It uses the same motors, same protocols, and everything is the same. So absolutely everything I'm talking about today in this video is applicable for this new robot. As I said, this robot has 6 different motors to control the position of this robot. And usually, to operate this robot manually, you use leader arm. So it's absolutely the same robot with just slightly different gripper. And you move one arm And the second arm called follower simply repeat all the actions. So that you simply like copy paste the positions of motors from one arm to another. But if you want to control it using LLM, it's much more complicated, you know. So the position of robot is set by simply positions of all the motors. But as we discussed, LLM can only generate some text and can kind of give you some reasonable next words and so on. And it's really hard for LLM without any fine tuning, without any pre-training to return the like positions of the motors of the robot that it never seen before to achieve some task. But what LLM can do is to give some like reasonable human readable commands. Like we want to let LLM tell the robot to, let's say, move forward 10 centimeters or move up 5 centimeters or tilt the gripper up or down or like open the close of gripper. And this is fine. So this is what LLMs are capable of, and they definitely can do it. So the first thing before we let LLMs to control the robot, we need to implement some, let's call it, intuitive control of the robot and transform the learn how to transform the simple human language commands into the motor positions. Try to explain what actually this motor does. So let's say if we change the position of this motor, robot moves like this. Is there like any simple intuitive word or simple intuitive explanation that can describe what's happening? Probably not. You will need like multiple words to describe what's actually happening here. The same for like this motor. So when we move this motor, a lot of parts of the robot are moving, and again, it's not very clear how to explain what this motor does in simple terms. And the reason why it's so complicated, because these two motors are not supposed to move separately. The main reason for these two motors to exist is like moving this motor in some linear space. So for example, if you want like this motor together with like gripper and everything that follows to move it up, we need to change the position of these two motors. If you want to move it forward, again, we need to change position of these two motors. So these two motors indirectly control the linear position of this motor. And this is their goal, and they always should be moved simultaneously to achieve this goal. And this is where we need what's called inverse kinematics. So basically, we need to find a way to transform positions of these two motors into linear position of the gripper and vice versa. So let's look at it in more details, and let's try to derive all the formulas that explain the inverse and forward kinematics of this robot. Let's discuss how we convert position of the motors into the linear position of the robot. Let's look at this picture of my robot from the side. We can see that robot has two main links, the one called shoulder and connects this motor with this motor. The second one calls elbow and connects these two motors. And we can control the position of these links by changing either shoulder lift, this is the angle controlled by the first motor, or elbow flex, this is the angle controlled by the second motor. What we want to transform these two angles, shoulder lift and elbow flex, into the coordinates of this blue point in this system of coordinates with x-axis kind of on the table and z-axis directed upward. And we want to transform both like angles to the linear position and linear position back to the angles. The first thing that we need to pay attention to is that this physical 3D printed actual robot links are not aligned with the geometrical links that we will use in the like simple modeling of how the robot works. Simply speaking, this motor connected to this motor and this motor connected to the next motor, and the actual kind of geometric link goes between the axis of the first motor and axis of the second motor, and then axis of second motor and axis of the third motor. But because of how the robot like works, this actual line that connects them is not aligned with the actual link. So whenever we kind of move between the actual physical position of this link and this link, we should add or subtract some offset that's shown as like small yellow arrows here. And we need to remember that in the most of the explanation going forward, I will use like these two red angles because they're much more convenient, and these two like red lines for all the formulas. But then when we do like final conversion, we need to make a little bit of adjustments to actually transform them to the angles of the motors that are controlled by motors directly. So let's denote them alpha1, alpha2, and lengths of these distances between the motor axis L1 and L2. Then again, let's add the coordinates to the picture, and let's try to find the coordinates of the blue point. So to find the coordinates of this blue point, basically what we need to do is project this L2 and L1 on the coordinate axis, on X and Z. If you want to find the X coordinate, we need to project them on the X axis. Violet projection is simply projection of L2 on the horizontal axis, and the orange one is projection of L1 on the horizontal axis. We can compute them by multiplying the L1 and L2 by the corresponding angles cosinus. In the first case, it's just alpha 1. In the second case, it's this small angle that is simply alpha 2 minus alpha 1, because this angle here simply equals alpha 1. By using this like very simple school level geometry, we can compute the X coordinate. To compute Z coordinates, we basically need to do more or less the same, but this time we need to multiply them by sinus of each angle, and we need to sum up this orange and violet lines. And when we compute Z coordinate, we should remember that we computing it from the ground level, so we also need to add this fixed H0, that is the height of the first motor. So these two simple formulas that computed using the simple geometry allow us to transform the original angles that we know from the motor positions into the linear coordinates of the robot, of this point in the robot. And these two equations called forward kinematics, and again, they exactly transform joint positions into the actual linear position of the model. But to really control the robot, we need to know the opposite one as well. So if you want the robot to be able to move when we tell it to like just lift up by 5 centimeters or so, we need to be able to transform the linear coordinates back to the angles. Let's try to do it. First of all, let's consider this extra triangle here, and let's compute this distance between the first motor and the third motor, and the distance simply computed using the Pythagorean theorem. We can see that in this triangle, consisting of two red and one orange lines, we know the length of each side, and we want to find this angle. And it's very easy to do because we can use the cosinus formula for the triangle and simply compute that alpha 2 equals r cosinus of this expression here. Then we can also find alpha 1. To do it, we can see that sum of alpha 1, the red one, and then this orange and green angles should be 180 degrees because they sum up into the straight line. It means that to find alpha 1, we can find just these two angles and then subtract some of these angles from 180. The first angle, the orange one, can be found from the same triangle as we used for alpha 2, using slightly different formula because we trying to find another angle in the triangle. And the green one can be simply found using arctangents from this triangle. And again, by combining all these things, we can compute alpha 1. Now, these formulas in the bottom, they represent inverse kinematics. It means that they transform the actual linear positions into the joint positions of the robot. If you followed my explanation precisely, you may notice that I made some mistake. Alpha 2 is computed from this triangle, but the problem is that there can be a case when alpha 2 becomes more than 180 degrees. And in this case, this triangle will not exist. It will be pretty different, and
you cannot compute Alpha 2 in this way anymore. To compute it in a more proper way, we need to slightly adjust the approach and don't really use this formula. Even so, in like most of the cases and under like normal conditions, it's still fine to just stick to this simple. The correct way to find Alpha 2 is a little bit more complicated, but we still can do it. The idea is that we can look at the same triangle as we originally looked at for these forward kinematics formulas. And from this triangle, we can find that this like small green angle, and then Alpha 2 is simply Alpha 1 plus this small green angle. And this like green angle can be found as a arctangents of this purple line divided by the orange one. So this formula over here, it's much better because it works even when Alpha 2 becomes more than 180 degrees. And it's better to use it in the real application. This is the formulas, and we will use these formulas in the code to actually control the robot. One extra note. The wrist flex has slightly specific angle because whenever we move the position of shoulder and elbow, the position of gripper, the angle relative to the ground will also change. If we don't change the position of this motor, the wrist flex, the angle between elbow and gripper will stay the same, but it's not what we want for the smooth control. So for the smooth control, let's say if your gripper is currently like horizontal, and then you tell robot to move a few centimeters forward, few centimeters up or down, you want your gripper to stay horizontal. So this wrist tilt should stay constant, not wrist flex. In practice, it means that whenever we adjust Alpha 1 and Alpha 2 that also have like impact on wrist tilt, we need to adjust the angle controlled by this motor. We need to adjust wrist flex. But it's very simple adjustment. So basically delta wrist flex that we need to apply is just delta Alpha 2 minus delta Alpha 1. And this is what we will apply for this correction in practice. I have open sourced all the code that I'm using today, and you can find it in this robot MCP repository. The link can be found in the description of this video. An important remark that while I was working on this video, the robot released a big change in the library. So my code will not work with the latest version of the robot, and you need to install the specific one specified in the requirements txt. But maybe in the future I will actually fix it and adjust it to work with the newest robot version. Let's quickly just go through this repository because we'll use it later in the video. So first of all, I created this simple README, so just follow it for quick start. You simply need to clone repository and install all dependencies from requirement txt, and after that you can start using the library. You need to do a couple of configuration steps to let it work with your robot. First of all, you need to either replace this file main follower.json or just change the path to this file in configuration, and this is simply the calibration file from the robot. So if you already calibrated your arm using the robot library, this library created this file in your repository, and you can simply copy paste the content of this file here. It's exactly the same file. And second, you need to update the config.py, and mainly you need to update two things. First of all, this calibration file. If you, instead of copying the content, just want to specify the path to your calibration file somewhere, just replace this part to the absolute path to your file. And second, you need to update the port of your robot. Again, just follow calibration and setup instruction from the robot. And one of the first steps is to find the port, and you need to put this port here to be able to deal with the robot. The rest of the config is similar to config in the robot, so it specifies motors for SO100. If you're using another robot, probably you'll need to update this one. And also you need to specify all the cameras that you're using. Again, format is taken from the robot, so it should be easy. You can just copy paste from the configuration that you already have for your robot. And then there are some specific parameters that you can also update. So the first one is the robot description and instructions that LLM will see whenever it requests them, and usually I ask it to request these instructions before they're doing anything. You can try to play with it and update them. Then some parameters that we use for forward and inverse kinematic, and some operational degree limits. So as I said, different motors have different limits that we want to use. Again, probably you don't need to touch it. And finally, some preset positions. I will demonstrate them a bit later. So most of these things you don't really need to touch if you already have your robot and configured it in the robot. You just need to copy paste the port and update either the content of the JSON calibration file or just change the path of this file. When it's done, you are ready to go. And then you can find multiple Python files in this repository. The main file that contains most of the logic is robotcontroller.py. If you want, you can go through it and learn how it's implemented, but basically it implements all the kinematics and all the control logic for the robot. And there are 3 files that you can run. First one is check positions, that shows the positions of all your motors right now. Second is keyboard controller that allows you to control your robot using your keyboard. And finally, MCP robot server. This is the actual MCP server implementation that we will eventually use to let different clients to control our robot. That's it for overview. Let's move to some practical things. After you installed everything and configured your robot, the first thing I would recommend you to do is to run check position script. This script doesn't control the robot, but it uses the same code from the robot control file to access the positions of the motors and print them on the screen. So when you run it, you will see these 2 sets of numbers. The first one is joint positions. These are the raw positions of each motor, and human readable state. These are transformed positions that we discussed before. So let's look at them one by one. So the first one is shoulder pan, corresponds to this first motor position, and corresponding human readable state is robot rotation clockwise degrees. They are simply the same number but just shifted by 90 degrees. So when you rotate robot to the left, this number goes smaller. When you rotate to the right, this number gets bigger. The second 2 numbers represent the position of shoulder lift. It's this motor, and the elbow flex, it's this motors. These are motors that are used in forward and reverse kinematics logic that we discussed. And the joint position changes the linear coordinates of the robot. So again, linear coordinates of this point relative to this point. It's the height and this linear position. So let's try to move it. But let's try to move it up. You see that height goes down, linear position stays approximately the same, and these 2 shoulder lift and elbow flex motors are changing. When we move forward, again, the forward position, linear position of the robot is changing, while height is not changing so much, and these 2 motors are also changing. The next wrist flex corresponds to position of this motor, and again, if we change it, you'll see that gripper tilt is also changing, but they're not exactly the same. So gripper tilt, as we discussed, is the relative position of gripper compared to the ground, and wrist flex is position of this motor. So for example, when I move it like this, the gripper tilt goes around 45 degrees, while wrist flex still stays close to 0. And finally, there are like 2 motors that control the gripper. So one is wrist roll that corresponds to gripper rotation degrees, basically the same. And the last is the motor that controls the openness of the gripper. So when it goes completely open, it will be around 100. When it goes completely closed, it will be close to 0. Make sure that all these positions are the same as in my video before you go into the next steps. If you see any differences, most probably you need to adjust the calibration of your robot. Otherwise, your MCP server will not be able to properly control your robot. After you made sure that the algorithm correctly reads the positions of your motor, it's time to test the manual control. Again, before we give the control to LLM, let's make sure that our inverse kinematics and other control logic is implemented correctly. And to do it, I implemented this keyboard controller.py file that allows you to use your keyboard keys to move the robot. If you run it, you can see some warnings related to calibration, but it's fine, it still works even with these warnings. Important things to check that your cameras are connected. So all the cameras that you specified in the config, the algorithm will try to connect to them, and it will tell you if connection failed. And then you can see some instruction for the controller, but let's just try to use it in practice and see. So first of all, you can move it up and down using some of the keys, and you can move them forward and backwards. Again, you can see that this point is moving horizontally when we do it, and nothing else is moving when I just press one button. Again, maybe like a couple of degrees here and there, but this is just specific of the robot. You can also do some other things like open gripper, close gripper. Let's rotate it. Yeah, rotate to different side. Yeah, so you can kind of open it and close it. And you can also rotate the whole robot to the left and to the right. You see a lot of debug information, a lot of info in the terminal. Generally, you don't need it, but if you want to debug it, and if you think that you have some issues, it can be pretty useful. Another thing that I implemented is some limitations. So when you control the robot using two-arm setup, when you have a leader arm, then you shouldn't care about the physical limits of the robot, because everything that you can do with the leader arm is possible to do with the follower arm. But when you control it using keyboard or using MCP, there can be a case when the coordinates of the gripper or positions of the motors that are sent by you or by LLM are simply not reachable. And it's kind of a problem, so this is why I implemented some limitations. So for example, if you move too much, let's do it like this. So if you move too much up or forward, it will just stop. So I also have some safety margin, so the robot will not go higher than this position because it kind of hits the limits. And the same will happen if you, let's say, go backwards. Okay, let's do it like this. If you go backwards, it also will stop because it says it's some of the positions are invalid and you cannot go there. So I kind of restricting the movements of the robot a little bit. Also, I implemented some preset positions. You can go there by pressing 1, 2, 3, and 4. It can be very nice and useful when you control the robots. For example, this is the initial position. This is position where a robot is kind of ready to start doing stuff. This is position when you want to grab something from the top. And this is position when you want to grab something from the side. These things are not available for LLM in MCP. I remove this because otherwise it requires a lot of explanation what exactly can happen. But I think it's very convenient to have some presets when you control the robot manually. Let's look at the actual MCP server implementation. This file is the wrapper on top of the robot controller that allows the MCP clients to interact with it. Let's look at the main parts of the code. So first of all, we define our MCP object, and we need to choose some name and the port that we will use to connect to our server. Then we have some helper functions. I will not discuss them. So all the most important for MCP functions have these decorators on top of them. We don't implement any MCP resources, even so some of these things can be implemented like them. We implement everything as MCP tools. And if you want to make any function an MCP tool, you just need to add this decorator on top of it. and specify some description that will be available for the LLM, and then implement the function itself. So our first tool is very simple. It's just take the robot description from the config file and returns this robot description. The second tool is get robot state, and it simply takes the state of the robot, basically all the positions of all the motors, transforms it into some understandable, readable format using forward kinematics and some other conversions, and send it to the back to the client together with images from all the cameras. And also we have two main functions that actually move our robot. The first one has this very long description, and it is move robot function that accepts different move commands like move up, forward, tilt down, rotate clockwise, rotate the whole robot right to left, and basically it makes this rotation. So you can specify one or all of this, or like any of these inputs, and the code will use these inputs to actually rotate the robot. And again, in the end, it will return the JSON with the current position of the robot and all the images that are taken from all connected cameras. And the final function that we implement is control gripper. And this function is simply controls gripper. So if you send open as 0, it closes the gripper. If you send the open as 100, it completely opens the gripper. And that's it. Of course, there are like some cleanup functions implemented and entry points in the end, but these are technical things. So everything that has this decorator MCP.tool will be available for the LLMs, for the MCP clients to call and to use. So now we can see how it works in real life. Now we made sure that our manual control for the robot works, and also we implemented MCP server. But before we give LLM the power to control our robot, it's also nice practice to check our server in the developer mode using the special tool. So to do it, you just need to run this command mcp dev and then the name of the file with MCP server. Let's try to do it. It's starting MCP Inspector, and now you can just follow this address. So it's your local host and 6274 port in my case to work with this MCP Inspector. If you follow this address, you will see this web interface of MCP Inspector. And the first thing you need to do is to connect to your MCP server. So there are two options. The first one is using stdio, is the simplest one. The second one is to switch to SSE and streamable HTTP, but to do this, you need to run the server in the separate terminal. So we'll just do stdio. Let me connect. Everything connected properly, so at least we know that our server works. So you can see different functionality of the MCP that you can test here, but we don't have anything except tools. So let's try to list our tools, and you will see all the tools that are available for MCP client with their descriptions. And this is exactly what we wanted. So get initial instructions, get robot state, move robot, and control gripper. These are 4 tools that we implemented. You can click at each of them one by one and try to run them. For example, if we try to get initial instructions, this is what we get. It's the text of instructions that we provide and specify in config. So this one works properly. Now let's try to get robot state. When we do it, we get the robot position message that it retrieved properly, and also pictures from the cameras. So you can see currently I connected just 2 cameras to my robot, and it's wrist camera and forward looking camera that you can see here. And now let's try to move robot. This is our main tool. So let's try to move robot 50 centimeters up, 50 centimeters forward, and tilt gripper 45 degrees down. Let's run tool. You cannot see it, but robot just moved. And we see that parameters of the robot change, the head, linear position, and gripper tilt. Also, we can see in the camera that it's tilted a bit downwards, and the location of the gripper changed. And finally, we have our last control gripper tool. And let's try to open gripper. Let's try to set openness to 100%. Oh, now we can see that the gripper is open on the pictures. And now let's say close it partially to 30%. We can see that it's now much closer. And if you set it to 0, yeah, there is still some space, but it's fine. This is done intentionally, so it's never closed completely. So yeah, by using this MCP inspector, you can check if all the tools work properly. And it's very nice tool for debugging your MCP server.
Before we go to actual MCP usage by LLMs, it's very important to understand that it's not free. So this part of the experiment requires you to use some LLM API access, and in most of the cases you need to pay for this access, either when you use different clients or where you use like your own API keys and directly call, I don't know, Gemini, GPT, or Claude. So all of it costs some money, and this agentic MCP approach is also costly because we send a lot of requests to LLMs. These requests contain images use a lot of tokens and so on and so forth, so it can be not very cheap. So just be mindful when you run these experiments, and please control your spending, your budgets. I've been experimenting with my robot for like a couple of weeks. I think I reached all the limits that I set for all LLMs that I had, and I think I spent more on this API calls in these 2 weeks than this robot costed. So again, just be mindful, just don't forget to control your token usage, and make sure you understand the pricing before using any of the LLM tools.
The first client I wanted to try is Claude Desktop. Since Anthropic created the MCP standard, I expected the native desktop client will support all MCP features by default. But this wasn't the case in practice. So first of all, it doesn't support SSC transport for locally running servers at all. So it means that if you want to run your MCP server locally, you can use only STD-IO transport. It's not a big problem. So I managed to configure it. So basically I provided the path to my Python environment and the Python file that should be run. And you can see that it's currently available as a tool for the Claude. So it successfully ran it and can use it. But let's test it and see and look at another issue that we have with Claude. So first of all, let's ask it what is the state of the robot. If we do it, we will soon see some discussion. So yeah, we can see that it's actually calling get initial instruction tool. Then there was some issue with the second request, but the next request was fine. And you can see that we got the information about the robot state. But what we didn't get is pictures from the cameras. So there are no images here. And when I looked into the logs, I realized that the sandbox where the Claude Desktop running our MCP server probably doesn't have access to cameras. And I don't see any easy way how to let it use camera on Mac. So of course there are like some hacks how we can do it. We can run some specific gateway to do it, but it seems just a little bit too much. So simply speaking, in our setup, we cannot really use camera images if we use Claude Desktop as a client. It's a bit unfortunate because it means we cannot really test any like smart tasks that require any reasoning, but let's at least try some very simple things. For example, move robot 5 centimeters. So wait a second. you can see that robot moved and now 5 centimeters forward. Again, it's working, and then, I don't know, open the gripper. Oh, sometimes if you haven't used some of the tools yet, it will ask you to actually allow or decline using this tool. So it's also very important when you initially test your client to do it manually. So as you can see, everything works properly when we give simple commands, so it can really use our MCP. The only problem, it cannot get access to cameras, so we cannot really test any like smart ways to control the robots right now. So if you have good ideas how you can use cameras in this setup in the Claude desktop, please write it in the comments. I very interested to learn some nice ideas about it. But now let's move to the next client. One of the most popular LLM applications is coding, and some of the best LLM clients are IDEs. Today we'll test two of them, Windsurf and Cursor. Controlling a robot using a chat with an LLM inside an app that's supposed to be used for writing code doesn't really make much sense to me, but it's what MCP allows us to do, so why not? Let's try it. We'll start with Windsurf, and this time I will use Gemini 2.5 as a model. I already configured my MCP server in Windsurf, and you can check it by clicking on this tool button, and you can see that there is this MCP server available, and if you click on it, you can see 4 tools that we have implemented. So everything looks fine, and we can start testing it. I want robot to complete a simple task this time and grab this ball. Of course, this task can be solved by much simpler policy that you can train with, I don't know, 20, 30 observations. But here we are testing the like raw capabilities of LLMs to control the robot. So remember that there was absolutely no training. It didn't see how to control this robot before, and it's supposed to analyze the information that we provide, mostly the pictures from cameras, to achieve the goal. Now we can see that everything works properly. You can see that all 3 images from all 3 cameras are available for the client, and it's trying to complete the task by so far properly rotating towards the ball. So let's see how it goes. And you can see that it's right there from the top view, and we cannot see anything from the front view because the robot covers it itself. Okay, we successfully grabbed the ball, and finally it should lift it up. One more second. Yes, cool. It's successfully completed. You can see that LLM can really navigate and interpret images and control the robot that never seen. And overall, it's cool. In practice, I would say that success rate is not so high. With the good camera setup and everything, it can probably be around 50%. So in my experience, 50% it can grab this ball, in 50% of cases it cannot. And one of the main mistakes that it does is related to rotation. So movements forward, backwards, up and down in these linear dimensions are usually fine, but it's really, really bad in rotations, and quite often just missed and angle. Let's also look at the example of the fail. So I speed it up 3 times so we don't waste too much time. You can see that it's very easy. In this case, robot didn't even need to rotate much. It just needed to like grab the ball. But when it moved close to the ball, it pushed it instead of actually grabbing it, and then ball went out pretty far, and it tried again and didn't manage to do it. So yeah, like this happens on average maybe like every second time. But given that we're using models that were never supposed to actually control any robots, 50% success rate is not so bad. Now let's look at another client, Cursor. It's also IDE and have very similar interface to Windsurf. I'm using it with Claude 3.7, and I'm trying to do a more complex task. So I have these socks on the table, and I want the robot to clean it up, to take my socks and put them into the card box. And first of all, let's look at some fails, because again, they're pretty typical across different problems. So here it's very similar to the fail that we've seen with the previous robot when it's tried this previous experiment where it tried to grab it. It was very close, but then started to hit the object and so on, and eventually failed. So this is very common mistake. In my observation, usually Cursor with Claude 3.7 work pretty well, better than other models, and it can grab the object pretty often with a good quality, but then it starts to make other mistakes. So for example, here what happened, it grabbed the object, it lifted it, but then it started to hit the box. So it couldn't understand that it need to raise the gripper before moving, otherwise it will hit other objects. When I've seen that the robot makes this mistake quite often, I actually added it to instruction and said explicitly that whenever you move, try to leave the gripper to make sure you don't hit other objects. Interestingly, even so overall Claude is better than Gemini, turned out Claude is not very good in following these instructions and quite often ignore them, while Gemini was worse in grabbing objects, but better in instruction following, and it actually started to lift it. In this set of experiments, instead of top view camera, I used side view camera. And the picture that you see right now is actually the picture that is fed into the LLM tool. And I've seen quite often that robot makes a very strange mistake. You'll see it here. So robot managed to successfully grab the object, then it lifted very high and high enough to avoid the collision, so everything looks perfect. But the next things that happens, instead of turning to the left, it turns to the right. It's like completely strange and predictable and very easy to avoid. So I was surprised with this. I tried to understand what's happening. I tried to debug my code and find where I like missed left and right. I even asked in the chat the model itself why it's doing it, why it's moving to the right when the box is obviously on the left, and model couldn't answer me what's happening. But then I realized that model simply cannot interpret different points of view. If you look at this picture, then the box is on the right side of the picture, yes? But relative to the robot, it's on the left, and model cannot understand it. For the model, like box is on the right, and it means it should move to the right. So this is very strange kind of bug. And again, I encountered it like many times. It wasn't the only moment I've seen it. And then I realized that that the alignment of the cameras is very important. And if you have multiple cameras, it's better to make sure that right is right and left is left simultaneously in all of them. So here again, you can see that robot rotated to the right after successfully grasping the socks. So yeah, and then as a next step, I just switched to the top view for this problem. And from the very first try, it was a success. Finally, I achieved around 30% success rate for this problem using Claude Sonnet 3.7. So here you can see the top view, the very first try for the same problem. And now the box on the right on this picture is the same as the box on the right relative to the robot. And I think this helped to improve the success rate a lot. Let's look at it. Yeah, nice. We successfully completed the task. So you can use any LLM and client that support MCP. And here I'm demonstrating the GPT and LibreChat as a client. You can see that it's not very successful. It's not because of the client, it's because of the LLM. I didn't manage to get any successful results or any meaningful successful results using GPT. It was good in understanding and it could describe what's happening on cameras and so on, but it wasn't really good at control and did some strange stuff. But yeah, generally you can try other clients. I even provide some link to the repository that contains a very long list of different MCP supporting clients, and you can choose anyone you like and use it. Some of the clients can be nicer because, for example, we don't confuse them by telling that they're coding assistant and then asking to control the robot. So you can find better ones probably.
So far, as you can see, LLMs are not very good at precise control of the robot movements. So they can complete some simple tasks, but they're not extremely good. And you always can train a simple policy that will be able to control the robot and complete the same task much faster with much higher success rate. Does it mean that LLMs are useless for robot control? Actually, no. So even so, they're not performing too well currently in the examples that I'm showing. You need to remember that they were never trained to control these robots, and they were never trained for this embodied reasoning at all. And the main advantage of LLMs is that they have some internet scale knowledge, and this is how we actually can utilize them. And this is the strong side, and we can try to use it for more complex tasks that require a little bit of reasoning, knowledge, and so on. There is this concept of System 1 and System 2 that was proposed by Daniel Kahneman. And this is a theory about the human thinking, and it states that there are two systems in our brain, and the System 1 is the fast thinking system that is responsible for some unconscious, very simple actions, and System 2 is slow thinking system that required when we try to complete more complex tasks that actually require us to consciously think about the problem. And robotics researchers borrow this concept, and many state-of-the-art models use this approach of having two systems. System 1 is what actually controls the robot. This system predicts the actions, the actual motor positions or commands that are sent to hardware, and it's usually some smaller model that trained or fine-tuned for the particular robot. System 2 is something more general that has more thinking capabilities, more knowledge about the outside world, and it can analyze and decompose the problem into the smaller tasks and then send the smaller tasks to System 1 to execute. You can see this approach, for example, in Gemini robotics paper from Google or Pi 05 from physical intelligence or Groot model from NVIDIA. All of them have two parts of the model where one is working on problem decomposition into simpler steps and so on. And the second is actually controlling the robot and generates the actions that are sent to the hardware. And even in this case, where we don't really use any sophisticated architecture, we don't really have two models, two systems, and so on, we can try to kind of separately test the system two capabilities of LLMs by asking a little bit more complex problems or asking like robot to solve a little bit more complex tasks and see if the like internal reasoning, if this internal knowledge of LLMs actually help to complete this task.
Now let's try to do some task that requires a bit less of robot control, but more understanding of the real world. So I put can of Coke and a bottle of water in front of the robot, and I want to ask my robot, I want to say that I need to water my plants, give me something for this. And let's see what it will do. So it needs to understand that it's see in front of it some stuff that can be useful for the plants and watering. Get initial instruction, get in robot state, the pictures. Let's see what it can recognize. Oh, it see the, yeah, if you click on the thoughts, it can see that there is Coca-Cola and water bottle in front of it, and it correctly decides to go left where the water is. Now let's start from the same position, but say that I want to drink something sweet. Get instructions, it's supposed to get pictures. Yes, it's getting pictures. And it can see that this is Coca-Cola, and it wants to grab Coca-Cola. So yeah, again, I don't want it to really grab it. It's a bit hard because of camera on top. Camera placement is not the best for this particular task. But it correctly understood what it should do, and it moving towards the Coke can. And this is the example of the actual real world understanding that LLMs have because of the retraining on the internet scale data. Okay, another reasoning experiment. I put 3 different balls in front of the robot. The one is a baseball ball, another one is just this like orange golf-like ball that we used before, and the third one is this black squash ball. And I wanna ask robot to grab the ball that is used in the racket game. So to successfully complete it, it should understand what is the racket game. It should look at the picture, realize that only one of these balls actually belongs to the game where you use racket, belongs to squash. And let's see what it thinks about it. There is a white baseball, an orange golf ball, and a black ball. Racket games. Small black balls with yellow dots are used in racket sports like squash. So it's correctly identified what I was asking for, and now it's moving the actual robot to grab it. So you see that like this reasoning is something that you need some internet scale pre-training for. So you cannot really train like a small policy from scratch that will know what the squash ball is and that squash is used in rackets. Also, it's a bit struggling with grabbing it, but let's see. I hope it will manage to do it. Yeah, it's done. Cool. So yeah, this is a good example of the task that requires both some like reasoning, knowledge, and control of the robot. And as you can see, it successfully completed the task. And this is actually the first try, so I'm really happy that it managed to do it.
In our approach, we didn't have two separate models, we didn't have two separate systems, but again, these examples that I've shown today kind of demonstrate that raw LLM, without any fine-tuning, without any pre-training on robotics data and so on, they can be very useful for system too. So they actually understand the world around them, they understand the object, they can do like some chain of thoughts that, for example, understand that I was asking about squash ball and this is this small black ball, and so on. So they do have these capabilities without even like any extra pre-training. But they're a little bit lacking in terms of the actual robot control. That again is explainable because it's much better to fine-tune or train system one models for the particular robot, or at least train it on some robotics data to get much better results. So again, as I said in the beginning, this all this experiment is more like toy educational experiments. So I didn't expect very good results, but they do show you the real capabilities of the robot. One of the next steps can be to train a simple, maybe VLA model to actually control the robot and integrate it into MCP and kind of use the big LLM as a system 2 thinking module and the actual VLA that can complete simple tasks as system 1. I think I will try it a little bit later in one of the upcoming videos. So let's summarize some findings from today's experiment. So first of all, we tested the capabilities of LLMs to control the simple robot. And results are kind of mixed. So first of all, we can achieve some reasonable success rate of like 30 to 50% depending on the task using different models. I think that Claude 3.7 is pretty good at these problems. Gemini a bit worse, but also performs well. Chat GPT, at least in my experiments, wasn't as good as other models, but at least it can interpret what's happening. It can plan what's supposed to be done, but it was like a bit worse in the precise control of the robot itself. And we discussed the system 1 and system 2 split, and again, all of them seems to be pretty good at system 2 thinking, but for system 1 we need something more. We need like better models that are more like fine-tuned and trained for this particular problem. It's actually very interesting because this is what we can achieve without any extra pre-training, but there are already some research groups that are fine-tuning all these LLMs on the actual robotic problems, and it's usually called VLA, the models that are basically VLMs fine-tuned for robotic tasks, and they are currently the state-of-the-art approaches for the robotics problem. So it's like very, very interesting area. I think it will be definitely integrated into the actual LLMs. So all this like embodied reasoning seems like a type of data that is underutilized currently for LLMs training. So I'm looking forward to seeing better LLMs with real world physics and embodied reasoning understanding. I think it will be pretty cool. On the way, we discussed other interesting topics. For example, inverse kinematics of this robot can be used in other applications. If you want to make your own teleoperation device or integrate some controller for teleoperation, you can reuse all this logic and it will simplify the control a lot. On the other hand, we talk about MCP and this protocol, how it can be implemented. Again, I don't think it's supposed to be used like this. I don't think it's supposed to like control the real robots, and I don't think it's the actual idea that is behind MCP protocol and how it should be used. But again, it's simply speaking some kind of API for LLMs, so why not? and we shown that it kind of works even for this unusual case. Even so, as I've shown you, the protocol is a bit thrown. All the clients, all the functionalities have some limitations. It's not implemented everywhere like 100%. So it's still pretty much in developing stage. So again, I'm pretty sure it will be improved in the future. But overall, works pretty well for this extremely unusual use case. That wraps up today's experiment. If you enjoy such deep dives, please like and subscribe, and also share your thoughts or questions in the comments below. Thank you for watching, and we'll see you in the next one.